So logarithmic decrement is defined as the natural logarithm of any two successive amplitudes in the same side of the mean position in an underdamped system. It is denoted by this symbol. So the ratio of any two successive amplitude in an underdamped system is always constant. So now this is a displacement time graph for an underdamped system. You can see initially this is the amplitude x0, followed by an amplitude of x1, x2, and then x3. Okay, so now the displacement in an underdamped system is given by x equals capital letter X e raised to power minus damping factor natural frequency t sine into bracket omega d t plus phase angle. So we already derived this formula when we were treating underdamped vibration. So this is the displacement for an underdamped system. So we're able to derive it in the previous class. So this equation is an equation of harmonic motion in which x e raised to power minus damping factor natural frequency multiplied by t is the amplitude, and omega d, which is the angular frequency of undamped vibration, is the angular frequency. Now, the maximum amplitude in a cycle will occur when sin omega dt plus phase angle phi is equal to unity. So that is this, sin omega dt plus phi is equal to unity. Also, the factor e raised to power minus damping factor natural frequency multiplied by time indicates that the amplitude will go on decreasing exponentially with time. Okay, so now the maximum amplitude is given by x equals capital X e raised to power minus damping factor natural frequency multiplied by t. So now this is equation 2, where since this is equation 1, so x1 is the maximum amplitude when we have t1, and then x2 is the maximum amplitude when the time is t2. You can see we had those values in the graph we talked about initially. That's the underdamped graph, the displacement time graph for an underdamped system. So now substituting these values in equation 2, so instead of x we now have x1, instead of t we have t1. So the same thing, instead of x we have x2, instead of t we have t2. So hence the ratio of two successive amplitude, which is, from that graph we had amplitude of x0, amplitude of x1, amplitude of x2. So now we are considering the ratio of two successive amplitude, x1 and x2. So we already know x1 as this, we also know x2 as this. So automatically capital X is going to cancel out capital X. So we are left with e raised to power minus damping factor omega n t1 over e raised to power minus damping factor omega n t2. So now using indices, of course this is your division sign. So instead of division, we are now going to have minus here. So that makes it e raised to power minus damping factor omega n dot t1 minus open bracket, then minus e raised to power minus damping factor omega n t2. Okay, so now of course minus times minus is plus, so and that's how we have this plus here. So when we now factorize, damping factor is common on both sides, natural frequency is also common on both sides, and so we have e raised to power damping factor omega n, then t2 minus t1. That's equation 3. So now t2 minus t1 can be referred to as the period of oscillation, or time period, or the time difference between two consecutive amplitude. So T2 minus T1 is given as TD. Okay, so now your TD is given by 2 pi over omega d. Of course, your omega d is the angular frequency for undamped vibration. So hence equation 3 now becomes, this is equation 3. Equation 3 now becomes x1 over x2 equals e raised to the power damping factor omega n dot 2 pi over omega d. So that is to say, instead of T2 minus T1 in equation 3, we have replaced it with TD, and we know that TD is 2 pi over omega d, and that's how we have this. Now we have e raised to the power damping factor natural frequency 2 pi over omega n square root of 1 minus damping factor square, where omega d is equal to omega n square root of 1 minus damping factor square. Of course, you know we use this function when we're deriving the formula for displacement in an underdamped system. Okay, so that means instead of omega d, we are now using omega n square root of 1 minus damping factor square. Okay, so now this becomes e raised to the power damping factor, then omega n we cancel out, and we are left with 2 pi over square root of 1 minus damping factor square. Okay, so now this gives us equation star. So that's e raised to the power 2 pi damping factor over square root of 1 minus damping factor square. So this is equation star. So now, taking the natural logarithm of equation star, that's the natural logarithm of both sides. Of course, you know this is x1 over x2. So you are taking the logarithm of this, the left hand side, and then with the logarithm of the right hand side. So that means we are having ln of what? X1 over x2 equals the ln of the right side. So that means ln of e raised to the power 2 pi damping factor square root of 1 minus damping factor square. Everything will be equal to, because this ln will cancel out this e here, and then we are left with 2 pi damping factor over square root of 1 minus damping factor square. Okay, so the natural logarithm of any two successive amplitude is known as the logarithmic decrement, which is denoted by this symbol. So it means your logarithmic decrement is given by this, equals what? Ln of x1 over x2, which is equals to this. So that is to say, the formula for logarithmic decrement is given by 2 pi damping factor over square root of minus damping factor square. So, but if the damping factor is very, very less than 1, it means the logarithmic decrement decreases to this. It now becomes 2 pi damping factor. So now this is an example. We're asked to find the logarithmic decrement and the ratio of any two consecutive amplitude of a vibrating system, which consists of a mass of 3.5 kg, a spring of stiffness 2.5 Newton per mm, and a damping coefficient 0.018 Newton per millimeter per second. Okay, so we're given the mass of 3.5 kg, we're given the stiffness of 2.5 Newton per meter, which is the same thing as 2500. Okay, this is 2.5 Newton per millimeter, so convert it, it becomes 2500 Newton per meter. We're also given the damping coefficient as 0.018 Newton per millimeter per second. So after converting, it becomes 18 Newton per meter per second. So now the logarithmic decrement, the formula for finding logarithmic decrement, which is what we just derived, is given by this. Okay, so but we need to find what is the damping factor. So the damping factor is given by this formula. It's given by the formula damping coefficient over 2 multiplied by mass multiplied by natural frequency. Okay, so but this diagram is to tell you, is to describe what we have from the question. Okay, this is the spring, this is the damping coefficient, and then this is the mass. Okay, now the natural frequency is given by the formula square root of stiffness over mass. So getting the stiffness is 2500 while the mass is 3.5. So square root of 2500 over 3.5, so that makes it 26.72 rad per second. So damping, now we'll be able to calculate our damping factor, and that's 18, which is damping coefficient, all over 2 multiplied by mass, then multiplied by 26.72. Okay, that's using the formula. So now that we've got able to get the value of damping factor, we now substitute in the equation for logarithmic decrement, and now we have it as logarithmic decrement equals 2 multiplied by pi multiplied by damping factor, which we just calculated, all over square root of 1 minus damping factor square. So eventually our logarithmic decrement is 0.6105. It has no unit. So the next question says we are expected to find the ratio of any two consecutive amplitude. So of course we have x1 over x2 as the ratio. Okay, so now logarithmic decrement is equal to ln of x1 over x2 equals 2 pi damping factor over square root of 1 minus damping factor square. So now we can shorten it to, instead of we take ln of both sides, or your x1 over x2 is the same thing as e raised to power logarithmic decrement. And since we already know the value of our logarithmic decrement, we just substitute the value and then we punch the calculator, and then we have x1 over x2, which is the ratio is going to be 1.84. Now for this example, second example, we are asked to determine the critical damping coefficient, the damping factor, the natural frequency of damped vibrations, and then the logarithmic decrement, and then the ratio of two consecutive amplitudes of a vibrating system, which consists of a mass of 25 kg, a spring of stiffness 15 kN per meter, and a damper. So the damping provided is only 15% of the critical value. Okay, so from the question we've been given mass as 25 kg, we've been given the stiffness, we've been given the damping provided, which is 15% of the critical value of the damping. So that's 15 over 100 multiplied by critical damping coefficient. So it means our C is 0.15 multiplied by CC. Of course, C is your damping coefficient, but CC is the critical damping coefficient. So the first question, we're expected to find the critical damping coefficient. Now, the critical damping coefficient is given by CC, which is 2 multiplied by M multiplied by natural frequency. We already know M, and natural frequency is given by square root of S over M, where S is your stiffness, M is the mass. So you substitute the value. Eventually, the critical damping coefficient is given by 1224.7 Newton per meter per second. Now the second question says we should find the damping factor. The damping factor is given by the ratio of damping coefficient to the critical damping coefficient. So we already told that the damping coefficient is given the value 0.15 cc. So that means 0.15 cc all over cc. So cc comes to cc. It means our damping factor is given by 0.15. Now the third question says we're expected to find the natural frequency of the undamped vibration, and that is omega d. Of course, you already know the formula. The omega d is given by omega n square root of 1 minus damping factor square. Okay, you already know the formula for finding natural frequency, square root of S over n, and that gives us 24.5 rad per second. So now substituting to this value, we already know the damping factor is 0.15. So eventually, the natural frequency for damped vibration is 24.22 rad per second. Now also we are expected to find the logarithmic decrement. So this is the formula. So you already know the damping factor. So we just substitute the value of the damping factor, and then eventually your logarithmic decrement is 0.9533. Also, we are expected to find the ratio of two consecutive amplitude S1 slash S2. So S1 slash S2 is e raised to power logarithmic decrement, just like we did it in the first example. And eventually your value is, the answer is 2.594.